Everyone, today I want to talk to you about the very important, super important concepts in machine learning and artificial intelligence, especially nowadays. This is a concept of generative versus discriminative models. All right. Uh, I mean, this is a very popular and very actually old concept. This is an old debate. There are lots of the explanation in the internet. I find this explanation very confusing, especially for the beginners. So I'm trying to give you a very intuitive explanation and very comprehensive explanation of the difference between these two frameworks or these two school of thoughts. And I want to tell you enough to make sure that you guys will understand that if a model is discriminative or if a model is generative, and then give you pros and cons maybe, and give you some examples of the generative and discriminative models. Right? So let's start. All right, so the way we're going to start is as follows. I'm going to first tell you a setup. So here's a setup. We have a problem. We have a machine learning problem. We have a predictive problem, right? So what is the problem? We have some input data or some features or some predictors X, and we have output data Y or label or target variable Y, all right? And we want to predict or we want to classify Y based on these predicted features X. This is the problem. All right, so what's the setup? Predict or classify output. I'm gonna write different output or target in the parentheses Y based on input or feature or predictor. Let me just be consistent. Do it like this. X. So this is the problem that we are trying to solve. All right. This is the problem. Now, so this is the most of the problem in machine learning, entire problem in machine learning. That's where we're talking about the class of regression and classification. So regression is when the Y is continuous. This is when the output is continuous, and this is when the output is discrete. So that's like the entire problem that we are solving, majority of problem. 80% of problems we are solving in machine learning is about this, regression and classification type problem. Like majority of problems. We have unsupervised learning, but this is the majority of problem in supervised learning domain is as follows, right? All right, very good. Now, let's first start with talking about the discriminative models. So this discriminative models. All right, as the name suggests, we are trying to discriminate. We are trying to separate two classes or multiple classes, right? What do we do during the discriminative models? We are trying to estimate probability of output given the features, given the input, given the predictors. We are trying to estimate probability of Y given X. Okay, so in this setting, we are trying to say that, you know what, we have a class 1, we have a class 2. I don't know if this test data is it associated to class 1 or is it classified to class 2, right? So I'm going to calculate probability of p of Y equal to 1 given X, and I'm going to calculate p of Y equal to 2 given X, and I'm going to compare to see which one is larger, right? And then assign the class based on larger probability. All right, larger probability. So that's the whole framework during the discriminative modeling. Now, discriminative models, in a sense, some people call it is efficient. Why? Because in a classification or prediction, what I am looking for is probability of Y given X. So I'm directly estimating that. I'm directly estimating what I want. So many people say that this is actually efficient modeling. Directly estimating the conditional probability. All right. Now, in literature, usually, up to like most, not you, sometimes the discriminative models they give you a better performance than the generative models. I will tell you more about this. Some intuitive understanding to get it actually better. Now, some example of discriminative models are logistic regression. Logistic regression. Again, conditional random field. Conditional random field. Maybe traditional neural network, like definition of the MLP, multi-layer perceptron stuff, right? They are built for classification. They are built for the finding this decision boundary, optimal decision boundary. That's what they do. Okay, perfect. Now let's talk about the generative, and then I will compare and contrast it for you. Let's talk about the generative now. Generative model. All right. So generative model, they're going to generalize. What does it mean, generalize? You remember in the discriminative models, we estimate P of y given x, probability of output given the features predictors. In generative, we don't do that. In generative modeling, we are going to learn the probability distribution for both input and output jointly. Okay? So in generative models, we are going to learn the probability of x and y. Joint distribution of the input and output. So learn joint distribution. So in a sense, we are not really answering the problem directly, right? Hey, I'm looking for classify, I'm looking for a prediction problem, but what I'm doing, I'm learning a joint distribution. That's what generative models are. Because they serve different purpose. I will tell you more about when I compare and contrast them. Okay? But now, hey, at the end of the day, I want to do classification. So what should I do? This gets interesting. So based on the relationship between joint probability and conditional probability, I can write this one as follows. X given y times probability of y. Now, this x given y is called likelihood. Likelihood of this conditional probability, actually observing data given the observing the class, the features given the labels. All right, but I'm not looking for that, guys. I'm not really looking for this. So what am I looking for? If you want to do prediction or classification, you are looking for this one. This is the quantity that I'm looking to estimate. So now Bayes' theorem is your friend. What are we going to do? We are going to go ahead and say that, hey, probability of y given x is equal to probability of x given y times probability of y divided by probability of x. All right, look what we have here. In order to get this probability of y given x, you need to estimate probability of y. You need to estimate probability of x, features, joint distribution of the features. I didn't say we have x on the feature. X might be x1, x2, all the way to xn. Joint distribution of all the features. And then the probability of x given y. So this is much harder. By the way, this probability of x sometimes is very hard to calculate. Sometimes it's very hard to calculate. So usually to estimate this one, they said this is proportional to x given y times p of y. But still, nevertheless, we are not really solving a problem directly. So generative modeling, you estimate the joint distribution, and then from here, by probability manipulation and the Bayes theorem, you get what you want, probability of y given x. The discriminative, you directly estimate probability of y given x. Now, what are some examples of the generative models? Example, naive Bayes, hidden Markov model, hidden Markov model. GAN, generative adversarial network, the name suggests you. Bayesian network. All right, and many more. Great. So now we have a good foundation. We have a good understanding between generative and discriminative. Now let me tell you more. Let me tell you more now. All right. So generative, why do we uh, use generative modeling? Why do we use discriminative? Discriminative modelings are used when you are trying to actually find a classification. All this, the only sole purpose that you're doing is that classification or prediction. So I'm gonna write here another color, discriminative. Here I'm gonna write generative. All right. So discriminative model is for a sole purpose of classification or regression. It requires less computation, requires less resources, because you just saw that we don't need to estimate the full probability distribution, right? But what about generative? Generative modeling is used when you are looking for much more than the only classification or regression. When you are looking to generate entire data points, or entire sequence output in one go, is also used to generate synthetic data, synthetic synthetic data, yeah. Or in general, it is used to generate new data point, right? Because you learn the joint distribution. So you have, this is a good one. You learn the data generation process in a sense. Data generation process. So you learn the data generation process. Therefore, you can sample from that. You can sample from this, and this give you more data. All right? Look at this beautiful thing. Hidden Markov model. You learn the joint distribution of states and observation. So you can sample new data. Hey, I have it for 10 time points. Can I get the new data? Absolutely. I sample from the distribution of observation, the distribution of states. I get a new state. Then I find the probability of observation given a state. I sample from that. I get the observation. Then I want to sample from the probability of next state given this state. I sample from that. I go to the next state, right? This is the idea of a generative model. Now I want to tell you something more actually here. So now this is a compare and contrast about that. So this data generation process actually is very, very important. So you learn actually what's the underlying process that generates the data. And then based on that, you can actually generate the entire sequence of data. Now I want to actually tell you something about that. I will call it a bonus. I will call it bonus, but it's super important. Please actually listen to this part as well. It's for generative modeling. And so it's like a danger of using generative models. Danger or good things about using generative models. You know, generative models has the roots in the graphical modeling, right? Have you, if you like listen to what I have said up to now, you see that we learned the joint distribution. Then we learned the distribution of the um, conditional distribution by some probability calculation. Isn't this what very similar to what Bayesian graph or Bayesian network do? This is very similar to what Bayesian networks or graphical modeling do. Remember, you can represent any joint distribution using graph and Markov theorem, right? So, for example, probability of x1, x2, y, this is a joint distribution, can perhaps represent it using this. This can be one explanation of that, x1, x2, right? This can be one. This is, by the way, very naive base, right? This is going to be probability of y given x1. This is going to be probability of y given x2. Right? This is probability of y. This is probability of locally probability of x1 and probability of x1. You see? X2. So this is that you can generate the entire distribution. And if you want to write the joint distribution based on this graph, it's going to be what? It's going to be P of x1, P of x2, P of y, probability of y given x1, probability of y given x2, right? So if you want to write this one using the language of a graph, so you can represent any joint distribution using graphs. So the roots of generative modeling is in graphical model or Bayesian network, or sometimes looking at the Bayesian inference, right? The roots is at Bayesian inference. If you look at this one, for example, look at this graph. This is, by the way, guys, is a naive Bayes, very similar to naive Bayes. It's very similar to Bayesian network or Bayesian actually inference. This is a conditional probability or likelihood. This is like a prior. This is like a choice of prior. It can be like a prior, right? This this like a likelihood. This P of y given x1, like a likelihood, right? This is similar to naive Bayes, not exactly naive Bayes, because the direction of the arrows can be different. This is just an example, actually. So that's an example how you can show the distribution using a graph, right? All right. Now I want to tell you something very, very important here, guys. So I explained to you that generative model is used to generate a new sample because you learn the full distribution. But my question from you guys, or something to think about, that is, let's compare something here. Naive Bayes versus logistic regression. So if you want to compare generative and discriminative models, under what case one is better than the other one? Guys, if the assumption of the problem, if the probability assumptions that you make for your problem is a good assumption, then generative models are better. Then naive Bayes is better. It's gonna give you a better asymptotic error. If the assumptions are better, probabilistic assumption, the probabilistic assumption or distribution are reasonable for data, then naive Bayes is a good model. Naive Bayes is a good model. Otherwise, discriminative model or logistic regression is going to be a better model, right? Let me tell you something about that. George Box was a very famous statistician. He said a very important quote. He said that all models are wrong, but some are useful. All models are wrong, but some are useful. So if you consider it in the context of generative and discriminative models, hey, I give you more information. You learn the joint distribution. You learn the distribution of the features as well. You learn the distribution features on top of the distribution of the output given input. So you learn more, right? So this is very useful. But what if what I learn is wrong? Then it leads to a really bad estimation. This is how you should think about that. Yes, naive Bayes give us more information than logistic regression. Logistic regression is only a classifier. But I will write what I said here. Note, this is by George Box. Is a famous statistician. All models are wrong, but some are useful. Some are useful, right? It's very, very important. So in a sense, the generative models, they give you more information, as I said. But if those information, so they are useful, they give you some information. But if those assumptions are wrong, then they give you worse performance than logistic regression. If the assumption probability distribution for naive Bayes is not reasonable, then logistic regression is a better choice. That's it. That's how you make a decision. All right. So that's the explanation that I have for the generative and discriminative. I could tell you much more, but I think actually this is good for the introduction. Leave a comment or question. I will do my best to answer your question. If you like my content, please subscribe to the channel, like and share it with your friends. Help me actually post more content. And I will post more contents about this generative and discriminative in my next videos. But let me know what other contents you guys would like to hear. I would like to talk about the stuff, even if it's high level, but in detail, or like a very comprehensive view of the material. Thank you so much for listening, and see you in the next video.